All right, so again, I'll post those examples later just to make sure we don't run out of time today. Now, getting in the 4.5, what we're talking about is L'Hopital's rule. And if you're just joining us, I'm going to postpone those two examples for 4.4, the ones where we use the graphing. I'm going to save that for another time. I want to make sure that we get through 4.5, 4.6, and 4.7 today. We want to just stay on schedule. But what this is an application of a derivative to find limits. So we have a computational application here. And it works like this. The rule is going to work like this. Now, you might have encountered some functions, or you've maybe wondered if you've got a situation where if you try to compute a limit, you get something like infinity over infinity or 0 over 0. And so what do you do in that case? So here's L'Hopital's rule. So let's suppose f of a equals g of a equals 0. And f of x and g of x are differentiable on an open interval containing a. Now, in addition to this, g prime of x, I'm not going to want that equal to 0 on the interval and x isn't a. Now, this last part might be a little confusing. Recall that when we're talking, and we're going to be talking about limits in section 4.5. So what we're talking about with limits, we're not talking about a situation where x necessarily has to be equal to a. We're interested in what happens as we get close to a, as x gets very close to a. It's practically a, but it's not exactly a. So what we're going to have is this. The limit as x approaches a of f of x over g of x. And the problem with this, if we think back to this top condition here, ooh, now if you can see that, there we go. If you think about this top condition, one of the techniques we use for limits is we just substitute this value a for x and then do the computation. But if f of a and g of a are 0, well, that technique's not going to work in this case. But there is a way we might be able to make it work. And this is L'Hopital's rule, what I'm writing right here. Whatever this limit actually is, it's the same if we take the limit of the ratio of the derivatives. So that's going to be a huge help when dealing with these. So any questions about that? So let me do an example. So let's say we're going to do this. Now, if we try to compute this, you might say, well, this will be the sine 0 squared over 0, which is the sine of 0 over 0. Sine of 0 is 0, and sure enough, we get this form of 0 over 0. And this is what's called an indeterminate form. This isn't going to work. So what we're going to do is do L'Hopital's rule. d dt sine t squared. And this is a chain rule. You have an outer function, so it's going to be cosine t squared, because the derivative of sine is cosine, times the derivative of the inner function, that's going to be 2t. Squeeze this in here, so 2t cosine t squared. Then for the bottom function, well, that's going to be derivative of t, and that's equal to 1. So now we can say this using L'Hopital's rule. The limit as t goes to 0 of sine of t squared over t will equal the limit as t goes to 0 of 2t cosine t squared over 1. So that's what L'Hopital's rule allows us to do. So what we can do is now that substitution. We'll get 2 times 0 times the cosine of 0 squared over 1. This will be 0. Cosine of 0 squared is going to be 1. And this just turns out to be 0. So any questions about that? All right. So another version of this, it helps us deal with situations like 0 over 0 if we try to take a limit. But it also holds true it also works for limits where the limit as x goes to a f of x over g of x is infinity over infinity. Also holds for that as well. So let's see, let's pull out an example here. Let's say we do this. So let's do the limit as x goes to pi over 2, the secant of x, 1 plus tangent of x. Now, if we take a look at these, this is going to be equal to the limit of secant x over the limit one plus tangent x. Now, as you get closer to pi over 2, what's going to happen is this is going to infinity. Now, for secant, to kind of picture what's going on with secant, it's been a while since we've done this. You can take our cosine function. There's 2 pi. There's pi. And there's pi over 2. And where the cosine function crosses the x-axis, that's going to give us a vertical asymptote. And so we get something like this for our secant function. Let's see, there's a little problem with this one. The double-sided limit's not going to exist. So let me take a look here. So we're going to settle. And let's take a look at tangent. Let's double check these. So for tangent, we're going to have something like this. So this is going to place a little bit of limitation on our limits. If we approach from the positive side here, we're actually going to get a tangent with a negative infinity. If we approach from the negative side of pi over 2, we're going to get a positive infinity. For secant, if we approach, this is pi over 2 right here. If we approach from this side, here I'll get rid of the cosine function so it's a little clearer. We approach from the positive side of pi over 2, we're dropping down the negative infinity. If we're approaching from the negative side of pi over 2, we're going to get positive infinity. So this notation is a little bit problematic because here you don't have a two-sided limit. It is going to matter which side you approach. So what we can do, let's handle this starting with one-side limits instead. So we'll approach from the left. So if we approach pi over 2 from the left for tangent, what we're going to get is basically 1 plus infinity. And if we approach from the left secant, climbing up, we're going to get infinity. And 1 plus infinity is just going to be infinity. So what we're going to do, we're going to address this for the one-sided limits first. So now let's take a look at L'Hopital's. We got this infinity over infinity. So let's take the derivative of the secant of x. If we do that, we get secant x tangent x. Now let's take the derivative of 1 plus tangent x. And that's going to give us secant squared x. So what this is going to give us is the limit as x approaches pi over 2 from the left, or the negative side, of secant x 1 plus tangent x. Well, this will be equal to the limit as x approaches pi over 2 from the left of secant x tangent x over secant squared x. So we'll simplify this down. Well, we'll lose a secant, we'll get tangent x. Lose a couple secants, they'll cancel. And we're going to get something like that. And this will simplify down to the limit as x approaches pi over 2 from the left of the sine of x. And so this is equal to 1. So all right, there we go. But we've only looked at one of the limits here. So let's take a look at the other side. We've approached from the left. Let's approach from the right. So to kind of just bring everyone back up to speed, let's take a look at those graphs again. Take a look at tangent. So tangent does something, oh, sorry, not like that. Tangent is going to do something like this. It's a period of pi. So this is our tangent, and it repeats itself on and on forever. So we approach from the left, and tangent goes up to infinity. If we approach from the right, from the plus side, it drops down to negative infinity. So what this means is that if we take the limit, break up the limit of the ratios, the ratio of the limits. Well, this limit here, we're going to be taking the limit of 1 plus tangent x as we approach from the right of pi over 2. So that means as we approach from over here, this plunges down to negative infinity. So negative infinity plus 1, that's not going to change anything. So we get the limit pi over 2 positive of secant x over negative infinity. So it looks like we're headed towards another indeterminate form. So let's take a look at secant. So again, with secant, we can start out with our cosine function. And let me get a different pen for that. So it does something roughly like this. There's our secant, there's our cosine function. And then where it crosses the x-axis, we're going to put in vertical asymptotes. And now we insert our secant function. So let's take a look at what's happening as we approach pi over 2 from the right. So the approach from the right, this plunges down to negative infinity. So that means the limit as x approaches pi over 2 from the right of secant of x is also negative infinity. So what we're going to get for L'Hopital's rule is that the indeterminate form, in this case, is negative infinity over negative infinity. And that's fine. That's going to be okay. So we're going to do the same thing. Now we know the derivative. Secant x was secant tangent. That was our numerator, our denominator. Is going to be this. And so that means the limit, now we're approaching from the right. Using L'Hopital's, we can use the derivatives instead of the original functions, which is a huge help. And again, if you're just joining us, that's only if you have a 0 over 0 or infinity over infinity when you take your limit. And this reduces down, let's see, we have secant x, tan x, secant squared x. And that's going to reduce down. X approaches pi over 2 from the right, sine of x. And this also, I'll make that plus sign a little better. This also equals 1. So here's kind of an interesting thing. When you look at secant and tangent, so here's tangent. When you approach tangent from the left, you have a positive infinite limit. But when you approach from the right, you have a negative infinite limit. And then as we take a look at cosecant, we actually have the same thing. We approach from the right, I'm sorry, from the left, infinite limit, positive infinite limit, approach from the, approach from the left, infinite limit, approach from the right, negative infinite limit. And we can combine these functions and we can take, if we want to, we can evaluate these using two-sided limits or one-sided limits. What we ultimately found this turned out to actually be equal to 1. And this one, and again with the help of L'Hopital's rule, that was also equal to 1. So even though you might sort of look like, because approaching from the left in both of these functions gives you a positive infinity, approaching from the right gives you a negative infinity. It looks like the limits aren't going to match. When we actually apply L'Hopital's rule to the one-sided limits, we actually get the same number. And so that means we're free to say, because the one-sided limits are equal, we can say this. Even though initially it looked a little doubtful. So questions about that? All right, let me show you another one. Now this is a tricky one. Let me show you what's a little little simpler. So let's say we're going to do this. Let's see. All right, so let's say we have this. Now we've been having x approach a, but we're also going to allow for x to approach infinity. We're going to allow for that. Now, what could help with this one is this initially, if you try to sort of substitute, if you will, what you'll get is, and this is going to be some sloppy notation, please forgive, times e to the minus infinity. And if you take e, you give it exponents like -1,000,000, -1,billion, -1,trillion, this is going to 0. So this would essentially be, an infinity squared is just infinity, so an infinity time. Well, this isn't 0 over 0, and it's not infinity over infinity, so it doesn't look like we're in a good situation. But we can rewrite this. Oh, a little carried away. So 0 times infinity, or infinity times 0, this is another indeterminate form. And so the trick when you get something like this is to rewrite it. And so now this will become an indeterminate form, infinity over infinity, which means we can use L'Hopital's rule. So now we're free to use it. So we take the derivative of that numerator, x squared. We get 2x. Take the derivative of the denominator. We get e to the x. All right. Well, let's take a look. Has this made our lives better? Well, what we're going to find out is that this application of it is not going to be good enough. Because what's going to end up happening? The limit as x goes to infinity of x squared e to the x, according to L'Hopital's rule, is going to be this. But this is bad news, because again, wouldn't you know, it's infinity over infinity. Well, that stinks. So we're just going to apply L'Hopital's rule again. So we might not use it once, we might have to use it multiple times. So again, derivative of the numerator, derivative of the denominator. Okay, I think we're going to be good to go. So the limit as x goes to infinity of x squared over e to the x equals the limit as x goes to infinity of 2x over e to the x, which is the limit as x goes to infinity of 2 over e to the x. And now the limit, as x gets bigger and bigger, this whole thing goes to infinity. So you get basically 2 divided by infinity, it's going to be 0. So we finally get our answer. Had to use L'Hopital's rule, a couple times to get there. So any questions about that? So let's take a look at another one. Let's see here. So there's a certain kind that you do kind of have to watch out for. And it's something of the form like this. So let's say we have the limit. And as x approaches 0 from the right, 3x plus 1 over x minus 1 over the sine of x. So if you do your substitution, we're going to get roughly 3 times 0. It's really tiny numbers to the right of 0. 0 minus 1 over, this is going to be 0 again, sine of 0. I'm getting a little ahead of myself. But basically what you're going to end up getting, maybe I should be a little more careful. I'm going to keep the limit here. Not get too wild. And this will be the limit. Sine of x. So what you'll get is 1 over, and as this gets smaller and smaller, it's going to be going to 0. So what happens if you take the limit with 1 over something that's getting smaller and smaller, you're going to get infinity. If you take the number 1, because this will be 0, you get 0 plus 1 is 1. So there, I'll put all the steps in. This is going to 0, and this is going to 0. What you're going to get is infinity minus infinity. And that's just bad news. So what we're going to do in this case, we're going to combine these. So when we combine them, what we're going to get a little trick you can do. I always found this helpful. You can multiply across to get your denominator. Multiply crosswise. Multiply crosswise again, and there's the sign, x times 1. And so what this will give us is the limit as x goes to 0 plus, from the right, 3x sine x plus sine x minus x over x sine x. And if you substitute 0 for the x's here, you're going to get 0 over 0. And so this says when this has been made into this, now we can use L'Hopital's rule. All right. So again, we're going to take the derivatives of the numerator and the denominator. So this one, we're going to get a product rule. 3x times the cosine of x plus 3 times the sine of x. So the product rule right there. Plus cosine of x minus 1. Just cinch it all together. There's our numerator. Now for our denominator, it's going to be x sine x. Take the derivative of that. So x times the cosine of x plus 1 times the sine of x. So x cosine x plus sine x. So now what we're going to do is we'll take the limit as x approaches 0 from the right of our numerator over our denominator. So again, if we substitute 0, we're going to run into a little bit of a problem. If we do that, what we're going to end up getting 0 times 1, which is 0, plus 0, plus 1 minus 1 is, oh dear, 0. Then 0 times 1 is 0, plus 0. We get 0 over 0 again. So that means we got to apply L'Hopital's rule one more time. Hopefully just one more time. We'll find out. So let's take a look here. We're going to take the derivative of that numerator. Excuse me. And again, we've got a product rule here. 3x sine x plus 3 cosine x. Let's see, we have sine, so it'll be 3. Ooh, let me double check. This is going to be negative. Put a negative in there. Don't want to forget my trig identities. So we've got this, and we have 3 times cosine x minus sine x. Double check, make sure that makes sense. Okay. Cool. And then for this one, we'll take the derivative of the denominator. So negative x sine x plus 1 times cosine x plus cosine x for the negative x sine x plus 2 cosine x. And these we could have combined in the 6 cosine x. We could have done that. So finally, now we get to take our limit again. Hopefully it'll work. Certainly put in the effort. So now we put in 0. For all intents and purposes, we're pretty close to 0. 0, 0. This is going to 0 out. This is going to 0 out. This will be 6 times 1. This will 0 out. This will be 2 times 1. So we get 6 times, well, basically cosine of 0 for all intents and purposes. So you get 6 over 2, and finally, let me see, how did you get the second 3? Oh, so the second one, it's from taking this derivative, the derivative of 3 sine x. That's going to be 3 cosine x. That's where that's coming from. So these here are from the product rule. And this one here, no problem. That's where that one's coming from. So criminy, there you go. It's going to be 3 after all is said and done. All right. So the last thing to mention in this section really is just going to be the, let's take a look here. The last thing to mention in this section, and we've actually seen this before, but it's this idea. If the limit as x goes to a of the natural log of f of x equals L, then the limit as x goes to a of f of x is equal to the limit as x goes to a of e to the natural log of f of x. And this will be e to the L. Now again, we've seen this one before when we tried to evaluate x to the x. So let's see here. Let's try a different one. Let's say we have this. If I'm erasing too fast, please let me know. Limit as x approaches 1 from the right of x to the 1 over 1 minus x. Now, this actually becomes what's called an indeterminate form. Because if you just substitute in your 1, you're going to get, for all intents and purposes, 1 over 1 minus 1. And this here, I want to be careful writing it that way. It'll be the limit as x approaches 1 plus 1 minus x. And this will be 1 to the infinity. And this is another kind of indeterminate form. So what we're going to do is this. The limit as x approaches 1 plus. And this would technically actually be negative infinity. I think you're going to get a negative infinity there. We'll go e to the natural log x 1 over 1 minus x. So what this will give us is the limit as x approaches 1 plus. And this is a power, so we'll have 1 over 1 minus x to the natural log of x. Oh, forgot my e. Oops. So what happens here is our limit is going to hop up like this. So what we're going to get here is we're going to have to deal with this limit. Which is going to be negative infinity times a negative infinity, an indeterminate form. So what we can do is we can rewrite these so they're going to work with L'Hopital's rule. And the way we can do that, and again, these are kind of little algebra tricks that we can use. We can call the denominator 1 over the ln of x. And we can call this 1 over 1 minus x. We can do that. And so what this is going to do, it's a little complicated, but this is going to infinity, negative infinity, with the 1 on top. This 1's going to get decimated. It's just being made. This whole thing is just getting smaller and smaller and smaller. So this will be 0. And then this right here, this whole thing is going to negative infinity, this little 1 on top. It's going to get decimated. We're going to get 0. Now, let me check my algebra here. Let me make sure I didn't make a mistake. Double check real quick. Ooh, let me see one thing. Let me see. Let me check something here real quick. Being a little, let me see, I can do this instead. For just a moment. So we can go ln of x over 1 minus x. So that's going to be negative infinity over 0. And we could treat this. So this would be a, we need to make this a little different. Okay. The infinity. Ooh, that looks like a little problematic. Let me take a look. Pardon me, just a sec. I thought this was going to be a little easier than I realized, but let me just make sure I'm not making a mistake. Okay, that looks right. Oh, silly me. Okay, I'm making an error. It's there. There it is. That's the issue. So we get infinity times 0. I forgot. I keep thinking this was infinity. We're sending this to negative infinity. It's negative infinity times 0. Okay. Whew. Getting a little worried there. So the limit as x goes to 1 plus. And now we can rewrite this. We can call this, let's say, 1 over 1 minus x divided by 1 over the natural log of x. There we go. Now we're doing good. So what this will become, this is going to be going to 0. 1 divided by 0 is infinity. This here is going to 1, so that means the denominator is going to 0. 1 divided by 0 is infinity. So this is going to give us an indeterminate form. There we go. Whew. So now we can apply L'Hopital's rule. There you go. Sorry about that. I got a little confused there. So we take the derivative of 1 over 1 minus x. And I kind of like doing the little cheat on this. Call it 1 minus x to the minus 1. So I don't have to use the quotient rule. Times negative 1. So we'll get 1 over 1 minus x squared. So that gives our derivative of the numerator. Let's take a look at the derivative of the denominator. Well, the outer function is 1 over some function. So that's minus 1 over that function squared times the derivative of the natural log of x, which is 1 over x. So we get minus 1 over x ln x squared. So now we try to do our limit. Oh, sorry, it's 1 over. And so this will be the limit as x approaches 1 plus. This will be a negative x ln x squared over 1 minus x squared. So this is not going to make our life any easier, because if we plug in 1, what we would get is -1 times 0 squared over 0 squared. So we're still going to get 0, a 0 over 0. Well, we must persevere. So we do L'Hopital's one more time. Hopefully this will be the last time. So in this case, we're going to use the product rule. We get x times, and then we'll use the chain rule here, 2 ln of x times the inner part, 1 over x, plus ln of x squared times 1. Ooh. Is 2x ln of x times 1 over x. So that means our x's will go away. 2 ln of x plus ln of x squared. And for the denominator, we'll get 2 1 minus x times -1, or -2 plus 2x. So now, this is quite a problem. X goes to 1 plus 2 ln x plus ln x squared over -2 plus 2x. Oh no, we're going to get the same thing. We're going to get a 0 over 0. So for the sake of time, I'm going to stop here because I do want to get to the other sections. This problem's just going to go on and on forever. And there's a chance I might have made an algebra mistake, and that's why this is dragging out so long. So I'm going to owe you another example. I apologize. But let me show you one that's we've done before. This one's a little more appropriate. I owe you that example, so I better do that. And there's a chance there might be an algebra mistake. But let's say we have this. So this will be a 0 to the 0, which is undefined. And let's say we give it. Oh gosh, I don't remember. Natalie, let me take a look at that problem again. Let me double check. I'm thinking I might have made an algebra mistake and it threw everything off. So I just want to make sure I'm not going to go down into a rabbit hole because we're burning through time. So we can rewrite this as e to the natural log of x to the x. So we can do that. That's the trick that we want to focus on. The rest of this, we're just hammering through all kinds of nasty algebra. Don't want to waste too much time on that. So we have something like this. And so what we can do, oh, sorry, it's a 1 over x, my apology. It's a 1 over. Give you a second to correct your notes there. So we have x to the 1 over x. And this will simplify down. Ln of x over x. Now again, this is going to be problematic. This is going to be, there's an e here, right? So we're going to take, before we get to the problematic part, the limit as x goes to infinity, ln of x over x, and this is all a power of 8. Now again, this is going to be infinity over infinity. So what that's going to mean is we'll take the derivative. We're going to use L'Hopital's rule. This will be 1 over x. This will be 1. And so this will be e to the limit as x goes to infinity. And again, I took the derivatives here because this will be infinity and this will be infinity. If I let x go to infinity, 1 over x. And this turns out to be 0. So our answer is going to be 1. So that's the idea of using that e in the natural log. And again, I'll owe you that other example. I need to go through that and make sure I didn't make a mistake. But that's the idea of L'Hopital's rule. Any questions about that? All right. So let's go to section 4.6. So these are optimization problems. Oh, so what you do is you're starting out. Oh, no problem, no problem. You're starting out like this. And this is the trick that you're using. You automatically go e to the natural log of whatever function you're working with. So you've got your function here. Now it's here. And the thing is, e and natural log cancel out. So it's like we really haven't done anything. We're just giving it a different kind of look. And so by introducing it, this is where it's powerful. This is how it helps us. And why would we even bother doing this? This 1 over x pops down. And that's a rule with logarithms and natural logs. The power is going to hop down. And so you can get e to the ln of x over x. And then the limit will hop up here. Limits can attach to exponent functions like this. It's one of the limit rules from chapter 2. And then if you take this limit, this will become infinity. This will become infinity. So you need L'Hopital's rule to turn this to 1 over x, to turn this into 1. And then you can take the limit. Does that help? Okay, good, good. Awesome. No problem. It's just sort of a slick trick that lets you sort of do some more algebra to solve these problems. So optimization. There's going to be 5 steps they recommend with these. I'm going to go through 3 problems, and you'll see me go through the same thing. But first off, we're going to read the problem. You want to read it, understand what's going on. Second, we're going to draw a picture. Third, we're going to place variables. Fourth, we're going to write an equation. And fifth, we're going to look for critical points. So we're going to read your problem, get an idea what's going on, draw a picture, place variables in that picture, write an equation, and then we're going to take a derivative of this equation and look for critical points. So let me show you the first one. Once you do these, you get the hang of them. They're kind of fun. So the first problem is going to be this. So this is step 1. I'm just going to redo the problem. There's 800 meters of fencing. There's a plot along a river. The river forms one side of the plot. Find the largest area for this, and I should specify rectangular plot. I'm going to admit this is a little too good to be true. Basically, what somebody has done is they've given you 800 meters of fencing. And they're going to tell you, go out and make for yourself a rectangular garden. And you need to use the river as one of the sides of your garden. And the rest of the garden, this rectangular garden, you're going to fence it off using your 800 meters. Now, here's the thing. How should you portion out the 3 other sides of this rectangle so you maximize your area? Because there's infinitely many ways you could do this. So let's make a little more sense of this. Let's draw a picture. So here's the river. And here's your fencing. So the fencing from here to here to here, that's going to be 800 meters. So that's what you're going to do. The question is, should this be something like this? Is that going to maximize your area? Maybe something more like this. Does that maximize the area? Because however you fence this garden, that's the land you get to keep. So we want to try to figure out, would something like this work best? Maybe something more like this. Is that going to give you more area? So how we can break this down. Let's draw a generic garden. So what we're going to do, we can label these sides X. So those are unknown. So if those are going to be our unknowns, then the remaining amount of fence will be the 800 meters minus 2x. So if this side is x and this side is x, this will be 800 minus 2x. Now, any questions about that? I'll admit this section, there's a little bit of creativity you're going to get into. All right. Step 4, we're going to come up with an equation. You could make it a square. That could be what it is. And we might discover, we'll have to see if it's going to be a square or not. But it could be a square. You would have something where 3x equal 800. But let's try something. Let's try this. Let's say we want to maximize the area. Now, these could be very tall, for all that I know. They could get so tall that basically this sort of gets taller, narrows in, like you're saying. So it's more shaped like that. This would be x. This would be x. It would still be 800 minus 2x. You would still have that on top. What you would be saying is that 800 minus 2x would also be equal to x, or again, 800 is equal to 3x. But whether it's a square or a proper rectangle, you're going to use the same descriptions for the sides. So whatever this is going to be, rectangle or square, the area is length times width, or x times 800 minus 2x, or the area is 800x minus 2x squared. So for your equation, whether it's going to be this or this, that's going to be your area. So for step 5, we want to maximize this. So that means you want to find the critical points. So we're going to indicate dA dx because we're interested in maximizing our area. So this will be 800 minus 4x. And since we're looking for critical points, we want to find points that make this either undefined or 0. Well, there's no division by 0 possibilities. There's no square roots to worry about. So we'll just set it equal to 0. And then we can solve for x. And we'll get 200 is equal to x. So questions about that? Now what that means though, that means this is 200, this is 200, and 800 minus 2x, well, x is 200, so this is going to be 400. So let's take a look. If we compute the area, 200 times 400 is 80,000. And then now, let's say they were the same. Let's compare this to if we had a square here. Well, that means each length would be the same size. This would be 800 divided by 3, which is about 266 2/3. And if we compute the area, what we'll get is 71,000. There's a repeating 1 there. So we actually get a smaller area in this case if we go for a square. So any questions about that? All right. Now, how's everybody doing? I hope I didn't wear you out in L'Hopital's rule. I'm a little concerned that I might have been strained a bit. All right. So another one, let's say we're going to do this. We're going to create an open box. It's 20 inches by 20 inches. Well, let me back up here. Open box using cardboard. That's 20 inches by 20 inches. And so what we're going to do to make this, now open box means we don't have a lid on it. So to make this box, and I'll draw a picture of what this is going to look like. We're going to cut out squares from the corners. So you might have seen this before, but what we're going to do We'll take our 20 by 20. And we're going to cut out squares. And then you'll fold it along these lines here. So we're going to remove these. So we're doing step 1 and step 2 until we get something like this after folding up the sides. So we're going to try to come up with something like this. Now the question we're going to ask, how big should these squares be to maximize the volume? So how big should the squares be to maximize the volume? So any questions about what we're going to try to do? So what we're going to do, we're going to start out with our piece like this. And then what we're going to do, we're going to label the dimensions of the squares as our unknowns. X, 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 and X. So this square is X by X. We're going to cut this square out. Same for these other squares. So what this means, this is 20 inches. So that means this part here is 20 minus 2x. The same thing on this side. There's 20 inches. And this piece will be 20 minus 2x. So any questions about that? So if we fold this box up like we intend, what we're going to get is 20 minus 2x, 20 minus 2x, and x. So does that make sense? It might take a while to kind of absorb it. All right. So we want to maximize the volume. So here's our equation. The volume of a box is the length times the width times the height. So we get 20 minus 2x, 20 minus 2x times x. And if we simplify this down, what we're going to get is 4x cubed minus 80x squared plus 400x. So this is the volume as a relationship with x, the size of one of the sides of the squares that we cut out. So now we want to find the critical points. So we want to take the derivative, and we're going to get 12x squared minus 160x plus 400. And we're going to set this equal to 0. So we're going to solve 12x squared minus 160x plus 400 equals 0. And that is, again, to find the critical points. If I'm racing too fast, please let me know. So when we do that, we can use the quadratic formula. And it's going to be kind of a messy calculation. But what you'll get is x is either 3.3 repeating, and x is 10.083 repeating. So you're going to get two answers, but one of these won't work. One of these doesn't work. And the reason is this. Note. Our box is 20 minus 2x. 20 minus 2x and x. If we let x be 10.083 repeating, we'll get 20 minus 2 times 10.083 repeating. And what that's going to give us is a negative number. So it comes out to approximately negative 0.166. So what that basically says, if we let this be the x, the dimension on our square, it's going to be too big. That means the sides and the length of our box will be negative 0.166 inches. So that side's not going to work. That size, rather. So the answer, the x is 3.3 repeating. So any questions about that? I have one more example to do, so I'm going to go about 10 minutes late. And then that's going to be it. We'll stop. We'll get through 4.6. We have a little bit of wiggle room. Maybe this is for the better, so I'm not overwhelming you with homework over the weekend. We'll go about 10 minutes over today just to finish 4.6, and that should keep us on our schedule because we do have a little bit of wiggle room. So at noon, yeah, I'll just do example. We'll have to follow the number scheme. So at noon, ship A is 12 miles. Technically 12 nautical miles or 2,000 yards. 12 nautical miles north of ship B. Ship A is sailing south at 12 knots. And ship B is sailing east at 8 knots. So a question they're going to ask on this one's it's got a little funky trick to it. We want to come up with a distance formula between the ships. I'm going to find a formula for distance S between the ships in terms of time t. So how would you do this? Well, one thing I'd recommend, let's place this on a rectangular coordinate system. So let's talk about noon. At noon, there's ship A that's directly north of ship B. And ship A is located, say, at 12. B is going to be located at the origin. So we can start it out like this. Now, what we want to do is let's look at how these ships are moving. A is moving south. B is moving east. So a question we can ask is this: how are the coordinates for the ships changing? So as time passes, how are the coordinates for these ships changing? Because if we think in terms of coordinates, we know how to find the distance between 2 points using coordinates. We can use the distance formula. So for ship A, Well, for ship A, it's just moving south. So X is going to equal 0. Now for Y, though, the ship's going to start at 12, but then it's going to keep heading away from 12. It's going to be heading down. So that means we're going to be subtracting. And it's moving down at 12 knots. Or I think that's nautical miles per hour. So for every hour, it's going to move 12 knots. So this amount we need to subtract from where it started on the y-axis. So in other words, as A travels south, it's going to become negative. Its y-coordinate will become negative as we keep taking away from this location here on the positive y-axis. We just keep dropping down. Now, questions about that? That's a little slippery. Now for B, y is equal to 0 because B is just traveling along the x-axis. But for X, we're going to take the starting point of 0 and add to that, since we're going in the positive direction, 8 knots times the number of hours it's traveling at 8 knots, or 8t. So questions about that? All right. So what this means is this. To come up with our distance function, we're going to have two coordinates. 0, 12 minus 12t. That's for ship A. And then B, ship B is 8t, 0. And so what we can do, we need the distance formula. So this time it will be s square root x2 minus x1 squared plus y2 minus y1 squared in this case, so 8t minus 0 squared plus 0 minus 12 minus 12t squared. And when you simplify this down, what you're going to get is s is the square root 208 t squared minus 288t plus 144. And so that's going to give you distance between the two ships. All right, just need about a little more time. We're almost there. So the last thing for this question, where do derivatives come into this? And so what we'll do is find a formula describing the change in distance between these ships. So all that's going to mean, we'll take the derivative of this. ds dt will be 1 over 2 times the square root 208t squared minus 288t plus 144 times, or using our chain rule here, you take the derivative of this, which you'll get is 416t minus 288. And so this will simplify down to ds dt is equal to 208t minus 144 over the square root 208 t squared to 88t plus 144. And that's going to be your answer. Whew. So that's it. I apologize for that bit on L'Hopital's. I didn't think it was going to take that long. And I'll take a look at that one example. I'm thinking I made some kind of algebra error and it went down a rabbit's hole. So I'll go track that down and try to get that resolved. But that's it for today. I'll get that example posted as soon as possible. If any questions, let me know. I'll make one more adjustment on the homework. Other than that, have a wonderful afternoon.